Hello, I'm Dr. Konrad. I'm a passionate physics lover, and these two are my fellow students.
Hello.
Hello.
Today, we want to talk about a special kind of physics the physics in Hollywood. Short question: was someone in the last days in the cinema? Probably not, because we have this annoying thing called Corona. But you all love and know it. So you're probably familiar with the feeling you're sitting in Avengers 10 or Star Wars, I don't know, 21, and there is this one scene where you think, is that possible? No, it can't be. This shit would never work in real life. Today, we have prepared a few scenes which we are going to analyze.
To begin, we will watch an iconic scene from Ocean's 11, the laser dance. Wow, impressive. A man dancing through the randomly placed lasers. Now I have to ask you guys, what is wrong with this clip? First of all, you could question the placement of the lasers. A normal security architect would arrange them in a grid, in a way so that there is no way of meandering through them. The second thing that is wrong with this scene is that you can see the lasers, which are normally not visible to the human eye like this. To show you why you shouldn't see the lasers, we prepared a little experiment. This is normal tap water. It has nearly no particles within itself. If we let the laser shine through it, we will only see the green dot at the end, because there's nothing in the water that could reflect the light emitted from the laser. We can't see a beam like in the movie. But if we pour some milk in the water, we suddenly see the beam. That's because the light is being reflected from the milk particles. For the scene from Ocean's 11 to be realistic, there had to be dust or steam in the air, which I don't think exists in a clean fancy hall, which is probably clean as a lab.
What is also clean are the actions of the secret agent. He goes towards the window and methodically assembles his weapon. First, he locks together the stock and the barrel with the oversized silencer. Now he loads the weapon with a shiny 7.62mm NATO round, known for its absolute precision. The secret agent crouches and aims at his target. He releases the safety catch and pulls the trigger. The objective is neutralized. The secret agent steps from the window. His assignment is complete. Unfortunately for the secret agent, he is not very likely to go undetected. A 7.62mm NATO round is supersonic and would cause a miniature sonic boom, even if the muzzle blast was muffled. Yes, the miniature sonic boom is not as easy to pinpoint as a muzzle blast, but it's quite noticeable, which can still draw attention to the shooter. To silence the iconic is next to impossible. Muzzle blast noise can exceed 150 decibels at a sniper's location, which is as loud as a blacksmith hammer. Considering that the threshold of pain is circa 120 decibel, we can be glad that Hollywood doesn't actually reproduce the noise in the movies. In real life, soldiers, snipers and SWAT teams have earmuffs. Silencers are used in real life, not for stealth, but to ensure that everyone knows whether the enemy shot or a team member. Silencers are also used in raids on clandestine methamphetamine labs because a normal firearm produces a so-called muzzle flash, which can light volatile fumes. In this case, silencers serve as flash suppressors. But how do you guys know that we are telling the truth? Can a silencer really not be used for stealth? Sound is a form of energy transfer, and we could define loudness in terms of the energy per unit of time or power output, but it wouldn't give the complete picture. Sound waves travel outward like balloons expanding around their source. Some amount of a sound's energy is distributed on the surface of each wave. Since a wave's sound energy is fixed and its area increases with the square of the distance from its source, the amount of energy per unit of area in the wave declines rapidly as the wave moves away from the source. About the same wave area contacts a person's ear regardless of how far she or he is away from the source. The area, however, contains significantly less energy when the source is far away rather than up close, which is why a distant sound is not as loud.
Unfortunately, human perception of loudness is not linear with respect to sound intensity. In other words, doubling the sound intensity does not double the perception of loudness. The perception of loudness is, roughly speaking, logarithmic and is represented somewhat better by the decibel scale as follows.
B equals 10 log L divided by LO, where B is the relative sound intensity in decibels, LO is the sound intensity at the threshold of hearing, and L is the sound intensity of the noise.
Even the decibel falls short of being a true indicator of perceived loudness. The loudness of a noise also depends on its frequency or pitch. Sound measuring equipment, at least partially, accounts for this fact by using various frequency whiting filters. However, if we assume that a muzzle blast's frequency content is in the general vicinity of optimum hearing and that the blast frequency content doesn't change with loudness, then the unweighted decibel scale is a reasonable indicator of relative loudness. Let's see what happens to the relative loudness level if we reduce the sound intensity of a muzzle blast by a factor of 2. This means we are removing half of the energy from the sound waves. Using the above equation, we get the following.
B equals 10 log L divided by 2LO equals 10 log L divided by LO minus 10 log 2 equals B0 minus 10 log 2 equals 150 minus 3.0, which brings us to B equals 147 decibel.
Cutting sound intensity in half only reduces the relative loudness by merely 3 decibel. This would be barely noticeable. A good set of earplugs typically reduces noise by about 30 decibel, and so would reduce a muzzle blast from 150 to 120 decibel, still a very loud noise. We estimate that the innocuous sound made by a movie silencer is roughly 50 decibel, a whooping noise reduction of 100 decibel from the decibel level of a muzzle blast. In other words, a silencer has to reduce sound intensity of a muzzle blast by a factor of 1010 to give such a low relative loudness. This can be done with a very well designed and precision-made silencer using subsonic ammunition. However, even commercially available silencers are more likely to give a reduction of 30 to 40 decibel, similar to earplugs, than the incredible 100 decibel reduction frequently portrayed in movies, especially when used on high-powered rifles. In summary, we could say, no, a silencer doesn't work as promoted in the movies.
Wow, that sounds interesting, but I have prepared some even better scenes. I will talk about speeding things up. Does Hollywood speed things up the right way? We will see with the following clip from Pirates of the Caribbean 3. Captain Jack Sparrow from the Black Pearl, Captain Davy Jones from the Flying Dutchman. It's about this chest. In the chest, the beating heart from Davy Jones, which everyone wants to have. And now comes the hero of this, Orlando Bloom. He makes woman's heart beat faster. Bloom sees the chest and grabs it, runs through the saber fights, cannonballs fly everywhere, and now comes the moment, which he called the oh shit moment. The chest is now in danger, but their friends at the cannon come to the rescue. Accelerated is not the cannonball, but the monkey jet. The monkey is launched, impact, the scene is safe. Does that really work? We'll find out now again with taking the time. We'll watch it again and launch. T equals 0 seconds. Impact 2.7 seconds. Can a monkey get from ship to ship in 2.7 seconds? We are scientists, we are physicists, we do the math. Between the Flying Dutchman and the Black Pearl, estimated 50 meters. We go back to the 7th class, v equals s divided by t. This gives us a speed of about 66.7 kilometers per hour. Now, when I ask if the monkey makes it from ship to ship, you say, what a stupid question. We still need to know the launch angle. Then we just conservatively put 2 degrees in the Cannon equation, or equation of the inclined cast. And now I ask you guys, how far does the monkey make it? Your answers were all wrong. The monkey makes it exactly 2.4 meters. We take the exact same equation, adjust for speed, insert the numbers and get about 83 meters per second or about 300 kilometers per hour. This is the speed the monkey needs to not fall into the ocean. I'm rarely at the zoo, but I've never seen a monkey fly through the air at 300 kilometers per hour. There are several reasons for this. Reason number 1, if you take a monkey and accelerate it to 300 kilometers per hour, in the time the monkey needs to travel 50 meters, there exists a so-called acceleration force, also known as g. Accelerating to 300 kilometers per hour in such a short time of 0.59 seconds corresponds to an acceleration force of 14.4 g. By comparison, an astronaut experiences a maximum of 10 g's during a rocket launch. Such a force would render any monkey unconscious, or at least incapable of fighting. The second reason why this action is impossible for the monkey is that such a cannon gets about 1000 degrees Celsius hot when fired, which monkeys usually can't stand. So in this case, Hollywood thought of something wrong. Dear audience, I hope you had fun watching this video. If you are interested in the sources of the music, pictures and information, or the stuff that was researched but not used in the film, or even the raw footage, you can have a look in the files which I uploaded to the Class 10 LearnSex file storage. If it was interesting, let us know, and please consider doing the same if you have any questions left.